Okay, we were talking a little bit about Higgs phenomenology yesterday. Here is a kind of textbook exercise that, however, I'm reminding you of because it has relevance for Higgs phenomenology tomorrow. Okay? So, if you take our theory that the Higgs theory, decoupled from all the gauge stuff that we wrote down yesterday in the 4-component scalar notation, so that the potential now looks like this. Then we can call the first 3 components pi's. These are approximately the same pi's that I was talking about before with you. And here, the 4th component, the thing that gets the VEV, we can think of as the Higgs fluctuation and the VEV. Okay? So roughly these are the same people that I was talking about in the last lecture. And we can look at what happens to pi scattering. Remember, if the Higgs has got a mass, in this Lagrangian, the pions are Goldstone bosons, they're massless. So we can ask, what is the scattering, just at tree level, what is the pi scattering that we get? And if you remember the nonlinear sigma model, because of the derivative couplings that it had, the non-normalized derivative couplings it had, it was going to give you something that went like energy squared over v squared. Okay? When you expand out the nonlinear sigma model, this is the kind of coupling you got. Of course, energy stands for anything. Momentum, energy, S. Okay. Now we can ask, what does this look like? I mean, this is the answer in the nonlinear sigma model. And we see this is not normalizable, negative dimension mass coupling parameter. This is a renormalizable theory, and you can ask, in what sense is this an approximation? And that's just a useful exercise. You can draw the 2 diagrams that you get, namely you actually have something that looks like this, but then you also have something that looks like this. And you end up with an amplitude that looks like lambda plus the lambda squared, v squared. So these vertices look like lambda v squared, and then again, I'm being sloppy about anything that's a momentum or an energy, and then lambda v squared. And indeed, if I am at very low energies and look at that amplitude, I indeed get the cancellation of the piece that's independent of momentum. But if I Taylor expand for small energy, Taylor expanding for small energy gives me this result. E is small compared to E. It's very small compared to lambda is squared. That's that result. On the other hand, for large energy, in fact, this behavior, instead of growing with energy, you can see is falling. So, this fact that we expected that somehow the renormalizable theory behaves better in the UV than the IR, well, it's true in this theory. Now, the fact is, experimentally today, we've discovered something that we're all calling H. And it seems to have couplings that, as we discussed yesterday briefly, they seem to roughly agree, all the rates, the different channels, but they seem to roughly agree with being the guy that you predict based on this model coupled to the electroweak gauge theory. But what I just want you to think about is, if you sort of think of this whole thing, the only reason that this bad behavior, in the sense of growing with energy or behaving in a non-normalizable way, the only way that it turns into the renormalizable behavior is by including the H. But it has to be an H with exactly the right couplings to come together to convert growth with energy into this more benign behavior. It's not good enough that the experimental object that we discovered has approximately the right couplings to do this job. It actually has to have precisely the right couplings to do this job. If it was only approximately the right guy, then eventually this strong coupling behavior would come back at high energies. Okay? So this is still an experimentally untested fact of whether this kind of scattering, which naively can grow with energy, where we believe that in the normalizable standard model would get cut off. We would say it gets cut off by the presence of the Higgs boson. But if this thing is not the Higgs boson, but approximately the Higgs boson, or only doing half the job and something else is doing the other half of the job of UV completing this theory, then this growth with energy will not get cut off just by this particle. And that's something that we could be experimentally sensitive to. Okay? Although that may be an ambitious program for the LHC machine itself. And I don't know the detail, maybe Martino has at least either worked on or has friends who worked on it. So there's something which is, just because this particle that we've seen is it's got so many coincidental features that match up with the textbook Higgs that it seems to be a pretty good bet that it's some sort of textbook Higgs. But there may still be other things going on involved in the UV completion, and we'll be talking about some of that, that say that it may only be an approximate textbook Higgs. And if it's only approximate, then this job of changing the high energy behavior is only being partially accomplished, in which case there may still be some growth of this amplitude. You might say that's all fine, but I can't do this experiment because these are pies that don't exist in the spectrum, right? But go out here. Indeed, it is something experimental. Remember, these pions do talk about something physical. They are about the strongest interactions of the physical object, which is the W bosons. And indeed, when we have protons with their quarks, we can do this. So morally, I'm drawing it like this, that the bits inside the W that are interacting the strongest, that's what we really mean by these fake degrees of freedom called pions. We can radiate off W's inside, in our scattering of protons, and we can try to perform this. Of course, this is also going back to them. So this famous statement of WW scattering, and which bits are these in the W's? The transverse degrees of freedom are the ones that would have existed even if we had not given the W boson a mass by the Higgs mechanism. So these pions are predominantly the longitudinal third degree of freedom that's there because they're massive particles. So this is the famous story, you could learn in great detail, of longitudinal WW scattering as the classic test of whether, in fact, quite apart from circumstantial evidence at lower energies, are you in fact getting a theory which is behaving in the ultraviolet like weakly coupled and weakly coupled and extrapolatable to high energies, or is in fact something else kicking in? Is it behaving badly? Is there a growth with energy of the scattering amplitude, which is only tamed at an even higher energy than the Higgs mass? Okay, so this is still something out there. Play around with it, as I say, it's sort of very simple, but the moral of it is still relevant. I want to switch topics. Okay. We're talking about extrapolating, we've been talking about the existence of a gap or a non-gap and all of that. One of the things you do when you have now got a model that looks like it can be extrapolated by the usual laws of normalized perturbation theory is to look at really extrapolating it and seeing what happens. Okay? If we trust that there's a gap, and we say, let's see what happens. Okay? Now, This brings in this subject of the renormalization group as a tool for extrapolation. Let me just quickly remind you why. So we're talking about energy is much bigger than the masses of the standard model, which we're doing as a theoretical extrapolation to see whether there's anything of interest to know, whether the theory can in fact be extrapolated beyond just saying that the theory is renormalized. So I remind you that in renormalized perturbation theory, renormalized quantum field theory, that the parameters of the theory are some masses, some couplings, okay, some masses, some couplings, and we have to introduce this notion of a renormalization group scale or renormalization scale, mu, okay? And we can say why we need that scale mu for various reasons. If you're just a very technically minded, but you want to do quick calculations, then you'd say, I need it because in dim reg, I need something to balance dimensions in some way, fractional dimensions, and that's it. Okay, maybe not a very insightful way to say it, but it's a pragmatic statement at least. More insightful is to say that it's the energy, it's secretly the energy at which the couplings G, if you think of these as your input parameters, well, we don't look up the textbook to see the input parameters. Some experimentalist goes out and measures these input parameters. And ME is secretly the energy at which the G was extracted, at which the experiment measuring G was run. Okay, if you're measuring the charge of the electron and you're doing it using some sort of Coulomb law, there's some separation that you decided to, I'm saying it in an almost textbook way. There is some distance between, you put two charges a certain distance apart, you measure how the force varies, well, there's some distance that you put them apart to make the measurement, at least over some range. And that introduces a length scale or an energy scale at which you measure. There's no way to measure these couplings without doing some specific experiment which runs in some particular index. So if you can think of this E as something like that, in on-shell renormalization schemes, in MS bar, this is what you're thinking. In on-shell renormalization schemes, this is what really this mu means. And if it has not come into your education yet, it should. You can think of it as sort of the Wilsonian cutoff. So if you've done statistical mechanics and you've studied things like the block spin renormalization group, then the notion of block spin renormalization group has an effective lattice spacing, and that is 1 over the lattice spacing is this mu. So there are deeply perturbative statements about what mu is. There are deeply operational experimental statements about what mu is, and there are deeply non-perturbative connections to other subjects about what mu is. This notion of the normalization group has it deeply embedded. Okay? So, this is the extra little feature that there has to be this thing. And the statement is that the choice for this mu is, in any of these things, arbitrary. An experimentalist could have tried to pin down which QED theory it was, what are the parameters of QED, by measuring the charge of the electron by doing different experiments. I could fix it using this experiment, you could fix it using that experiment. So another way to say it is that this theory corresponds to the same theory with some different choices of parameters, with some different choice of renormalization scale. Okay? When we do perturbation theory in this setup, we find a pathology. Okay, so perturbation theory gives us things that look like nice powers of the coupling, but it also typically gives us, perturbation theory is just the tip of the iceberg that we now understand more generally in non-perturbative physics, but let me just talk about that tip of the iceberg. is we end up with large logs, so that even though the coupling is small, in occasions these logs can be large. And in general, it's not clear whether you're doing a controlled expansion or not. And you might say, if you want, just keep in mind that this might be the energy at which you want to predict something. I want to predict the output of my theory is something running at some energy. And mu is secretly, if you think in this line here, okay, this is the energy at which you measured the input. So in extrapolating experimental data at one energy scale to vastly different energy scales, you will incur these large logs. There's no way to avoid them. And in what I would call robotic perturbation theory, you'll get them, and then it seems to undercut the validity of perturbation theory. Okay? So there's a puzzle as to what to do. And anytime you have a perturbative expansion, if you, and often enough they misbehave in one way or another, if you have a non-perturbative insight, which is qualitative, you can always improve your perturbative series. The information that you extract from perturbation theory may be flawed in various ways, at least being perturbative. And if you have a non-perturbative insight, you can always do better with the same set of calculations. This is true in many fields of our subject. The normalization group, this insight is a non-perturbative insight. The statement that this scale is your choice as to how to fix the theory, this thing shows this middle line here, and that the couplings and masses can be shifted accordingly, gives us a non-perturbative insight which allows us to improve this series better than just what the robot does. Okay? And that is what's called normalization group improved perturbation theory. And let's just, again, this is more textbook stuff, class stuff, formal classes. Let me just cut to the part that I want to bring out, because we'll use it now and then we'll use it in a more sophisticated form later. Let's follow the reasonable instinct that we neglect masses for a start, for energies much bigger than m, okay, which is where we're planning to go. In that case, we can ask, what happens if you choose a scale mu and I choose a scale mu prime, which is only infinitesimally different from mu? In that case, the G prime, the chain G changes infinitesimally. And so we get some function. There must be some relation between these G's, and that's given in total generality by this. This is just an infinitesimal version of this statement, of this theory and this theory. There exists some way of compensating G to compensate the change in mu, so that the two theories are actually describing, the two descriptions are describing the same physical reality. So at first it looks like this is it. Let's stick to the case that we've been studying, dimensionless couplings. Now that we've neglected the masses, we have these dimensionless couplings. Then by dimensional analysis, we can cross this off. Okay? Because you can't make a dimensionless function that depends on this dimensional scale. Okay? Now, trivial statement, but it is a non-perturbative statement, and so at least an all-ordered statement, and so boom, it's gone. And so we really are just doing this. Okay? There are several couplings. Okay. So if we're still at very high energies, we can work to order m even though masses are small, let's suppose I bother to keep track of these mass parameters, then similarly we can write now in total generality you could say there should be a well, here, if I'm working to order m, then okay, it's got to be something like that. And indeed, this makes it seem like g is a function of mu, and that's the couplings that we associate with having measured them at scale mu, we call g of mu. Okay, that's just the standard notation. These are called beta functions, so I won't change it. And these are called anomalous dimensions. In this case, anomalous mass dimensions. Okay. So in the standard model, we have a bunch of couplings. There's G, the gauge couplings for QCD, like SU2, SU3, SU2, and U1. There's the Higgs self-coupling. There's the big Yukawa coupling, which is the Yukawa coupling of the top. And then there's a bunch of really tiny couplings, which are much smaller. Okay? The Yukawa couplings of things which are not on the top. And so one can write down all the data functions and so on. I think in we can see, let me just give since it's relevant to thinking about pushing the standard model up to high scales, let me first just do the case of QED rather than the standard model. Okay, that's easier, where there's just one coupling. And this is an example of how you get a non-perturbative piece of information from a perturbative series by putting in the improvement that the renormalization group insight gives you. So in QED, the beta function looks like okay, now, which order 1 number is it? I forgot. So pretend that this number is 1 for now. You guys fix it. But the solution to this is very easy. It's that alpha at mu2 is equal to alpha at mu1, 1 minus alpha at mu1 over 16 pi squared, or whatever it really is, log mu2 over mu1. Okay, so this immediately shows one thing that we can see right off the bat, which is that if I were to expand this as a true series, then I should really say that it's alpha 1 plus alpha 1 squared over 16 pi squared log plus alpha 2 alpha 1 cubed log squared, etc. Okay? If I were robotically expanding in this alpha mu1. You can already see what I advertised earlier, which is that this is a series which has powers of alpha, it looks like perturbation theory, but it also has these large logs. That's the typical behavior in robotic perturbation theory. On the other hand, this formula has resummed, in this case in a very simple way, it's resummed the large logs into this quantity. And this is characteristic of one perturbative use of the renormalization group, although there's tremendous conceptual use that is also true of the renormalization group, which also gives you a non-perturbative insight. Why I'm doing QED is to also point out one thing, which is that as you go to high, if mu2 goes to infinity, or at least rises, you can see that the alpha, for example, the mu1 that we use experimentally is just the mass of the electron. Okay. But as we try to extrapolate QED to high energies, because this log is getting big, there's cancellation here, and so alpha 2 starts to go up too. And obviously, if you go high enough, you get to a stage where even calculating in this quantity starts to break down, because the alpha at very high energies, the alpha that you're, in the best case, the alpha to expand it, is itself becoming non-perturbatively strong. And so, the perturbative approach with this inside of the normalization group points to some place where QED, even though we think of it as normalizable, but ultimately something still breaks down, at least in our perturbative control. Maybe the theory is secretly safe for some strong coupling reason, but we cannot guarantee it just by weak coupling techniques. And what is that scale where alpha becomes so strong that we no longer trust perturbation theory? And exactly where you decide not to trust perturbation theory is your call. Is it alpha equals 16 pi squared? Is it alpha equals 5? It's your choice. But whatever that number is, fix it in your head. And you will see that the scale where you don't trust it will always go something like in other words, there's a quick and dirty way of saying where you don't trust it. I sure don't trust it when the coupling is infinity. Okay? That's a quick estimate. And you can see, it's easy to figure out where the coupling, this becomes infinity when this denominator vanishes, and if you solve that, this will always be a good estimate for any other choice you make. But it's e to the 16 pi squared over alpha and u1. So here's your fine structure constant, measured at some standard thing like an electron. And you can see this formula is not a power series in alpha. It's got 1 over alpha, even if you expand this thing. So this is some weird non-perturbative formula. Okay. We got it out of perturbation theory, but that's because we put in something non-perturbative too. And that was our insight into the nature of the normalization. And it tells you that even if it's a small coupling, there's some exponentially big scale way up there where the theory completely breaks down. You can't see it. A robot doing perturbation theory cannot see it. But we know that it's coming. Okay? So this is a deep insight that we have. Now it turns out, I bring that up only because, since we're studying standard model structure, that if we look, something similar can be seen in the beta function of the scalar self-coupling. So this Higgs self-coupling, if you look at its beta function, you see that it goes like 1 over 16 pi squared. And since I copied this from somebody else's group, oh, by the way, I was looking, there are many reviews on Wells has an interesting complimentary review to anything I'm saying. Jim Wells, and some things are discussed there. Since I just copied the formula that he had copied from somebody else, here are things with the right numbers. Y top squared. This is a very good approximation to the beta function of the Higgs. The Higgs talks a lot to the top quark, and so it's not surprising that happens. And in fact, if you thought that if lambda, remember, the mass of the Higgs goes something like square root of lambda v, right? So the heavier the Higgs boson, the larger lambda. When you go to heavy enough Higgses, lambda gets so big that these terms are subdominant. The top Yukawa is something like 1. These terms could become subdominant if only the Higgs boson were heavy enough. In which case, you could just look at this RG. This RG is qualitatively the same as that RG. And so, in fact, you would hit this kind of breakdown scale where at least the perturbative validity of the theory is broken down. This kind of a scale is called a Landau pole. Okay? So indeed, the Standard Model has a Landau pole in this case, where the Higgs boson is heavy enough, it will have a Landau pole. And in fact, the stronger the coupling, you can see it here, the stronger the coupling in the infrared, the lower the scale of breakdown, which means I cannot extrapolate beyond mu2, and the stronger the infrared coupling, the lower is this scale. Okay. So based on this, we can see already that there's a limit to extrapolating the Standard Model for sufficiently heavy Higgses. There's exactly, QED is replicated in the Standard Model even at high energies in the form of the hypercharged sector of the theory. So the hypercharged sector of the theory has exactly this kind of Landau pole as well. Okay? And if the Higgs was heavy enough, it would also have one like this. Now, as it turns out, having a significantly heavier Higgs, like 300 GeV, 400 GeV, would have meant that the Landau pole was not too far away. In which case, the Standard Model could not be extrapolated very high. But it turns out that nature has given us a relatively light Higgs boson, coincidence or fluke, okay? But such that, in fact, a better approximation is to neglect this and sort of think about this instead. Now, I am going to do scant justice to this equation by pretending that y top, which has its own normalization group equation, but I'm just going to pretend, just to show you what the issue is, I'm just going to pretend that this is a constant. Meaning it doesn't vary. I'm going to pretend that it doesn't vary, just to get the qualitative point that people talk about. What happens, why is this normalization group interesting when you have subdominant self-coupling of the Higgs and the top Yukawa takes over as driving the normalization group? Well, if it's constant, then even I can solve this normalization group. And I still have to look at my notes. The lambda of mu is equal to lambda. So lambda in the UV is lambda in the IR minus this 3 over 8 pi squared y top to the 4th log mu2 over mu1. That means that given this modest small lambda that we see in the IR, which means we see a small Higgs mass, given this modest guy, that if I keep running, eventually this term becomes big, and it's bigger than this, and eventually I find that the self-coupling in the UV becomes negative. Okay. So at some point, the picture you're supposed to have is, I start in the UV, or I start at short distances, with a potential that instead of looking like this, instead of a potential that looks like this, in the UV, it looks like this. It has both negative mass squared and negative quartic. Okay? This is what the theory looks like in the ultraviolet. And we are calmly, robotically doing the normalization group from mu2 down to mu1. This is my microscopic Hamiltonian, and now I am going ahead and calculating. This is crazy, right? If this is your microscopic Hamiltonian, then the theory is not just, here's what it is. The theory is not just sitting here and you're just doing this little story like this. That means you're doing the wrong, we know one thing's for sure, you're doing the wrong calculation. If you continue to believe the Standard Model, normalizable Standard Model, if you continue to believe it to scales where this takes over from this, and so that this is negative, then you are surely doing something terribly wrong. But then, that means that something is broken down. Something else has to happen. There are reasonable things that could happen. That there could be corrections, there could be new physics that makes the theory look like this, and so on. So, I am not a great expert on the subject, but it has been studied because estimating the scale at which this happens is, I gather the best estimates put it at around 10 to the 10, 10 to the 11 GeV. It's not the Planck scale, it's the geometric mean of the Planck scale and the weak scale level. Okay, so in terms of the span of energies that we're all concerned about, in a logarithmic sense, it's halfway. But you can read a little more about it, and some references and so on in this paper by, I think it's a paper by a large N number of Italians, including some of my favorite Italians. Okay, fine. It's interesting, provocative. I don't know any definitive answers that come by taking the standard model and running it up to high energies. I do know one other that does come by running up to high energies, and that is the thing that I want to spend a little time on. It's the subject of where you say that the electroweak symmetry breaking, which is a subject so subtle that I only touched on it in 3 lectures, but this is only the baby version of something much bigger at much bigger scales, and that is this idea of grand unification. So, in its simplest original form, the idea is that there is technically, in the group theory sense, I guess, a simple gauge group I do all group theory by analogy with SU2. So somebody asked me what simple means or semi-simple. I don't know, but it means that it corresponds to a single gauge coupling. The great group theory structure is such that you can't have 5 different gauge couplings. You can only have 1 gauge coupling. Okay. That's great. The input parameters in theory are down to 1. That's fantastic. Okay. So an example is SO10. That's the one I'm going to use, but generally it's this kind of thing. So imagine something like SO10, rotations in 10-dimensional Euclidean space. What could be easier? And this breaks down. Now it actually has as a subgroup the standard model okay, it breaks down to. And this happens just through a replay of the Higgs mechanism in all its glory. But it happens because some other, gut, so grand unified theory, gut, undergoes spontaneous symmetry breaking in the precise sense that we talked about in the last lectures. And this is happening at some scale above where the electroweak spontaneous symmetry breaking happens. So at this scale, SU2 cross U1 breaks down to U1 electromagnetism. At this scale, this grand unified gauge theory is Higgsed with some light gauge bosons and some very massive gauge bosons that are now way up there. Okay? But this is happening at some scale larger than this. Why is this sort of first even pushed into your hands? Why is this secretly the study of the standard model? Now it looks like I've just gone beyond the standard model, ran out of things to say. I said, no, this is definitely, I'm trying to really point back to the standard model and a puzzle that you must have in the standard model. And that is that the quantum numbers, we haven't talked in great detail about the quantum numbers of standard model fermions. So standard model fermion quantum numbers, in fact all the quantum numbers, are just coming to it. They look a little bit, what's the word? Bizarre. Bizarre is too strong a word. I can't think of anything else. They look strange, okay? And one wonders if one is seeing a pattern there or not. And so it is a very deep insight to say, I do see a pattern. And the pattern is they seem to fill out. Now I've chosen SO10, not SU5. That's for me, rotation groups. But anyway, they essentially fill out representations of this. They have simple quantum numbers under this. And then after all this processing down to low energies, you get something out that looks very bizarre. Okay? But instead of describing, I could sit here and fill a table with all the standard model quantum numbers. But the thing that surely matters about that is that there's such a simple relation with this kind of a grand unified group. In fact, if we include a right-handed neutrino, which is got standard model neutral. So if I just include a fermion that would be very, very hard to see if it was there, it may actually be part of the Dirac mass of the neutrinos of the real world. If I add this sterile neutrino component, then in fact all of these, every generation corresponds to a spinor representation of SO10. Okay? In fact, the spinor representation has 16 components. And 16 is exactly what one generation of standard model fermions, including the different colors, plus this guy, adds up to 16. It's not crazy to understand where the 16 comes from. Possibly useful. You can think of SO10 as containing two obvious subgroups. It's obvious that they're subgroups. SO6, where you rotate the first 6 guys in 10-dimensional space, and SO4, where you rotate the other 4 directions in SO4, but just within themselves. So this is a subgroup. Now, this thing is isomorphic to SU4. And indeed, if you want spinners of SO6, I can tell you what they are. They're just the fundamental representation of SU4. They're just 4s. 4s of SU4 are the spinor representations of SO6. So that one was easy. It's exactly like SO3 and SU2. Only to the group theory I know. And this, as I said before, is SU2 cross SU2. Okay? Left, right. So we've talked about that. Now, when you talk about spinners in higher dimensions, it's interesting. How do you construct the spin, even when you go from 3 dimensions, you have these matrices that you use to generate the rotations, the Pauli matrices. When you go to 4 dimensions, you like the gamma matrices. You could go to higher dimensional space-time and talk about some bigger gamma matrices. This is like trying to figure out how to think about the sort of the gamma matrices in 10 dimensions, Euclidean space. Okay. And there's an algorithm for generating from lower dimensions the gamma matrices and spin matrices of higher dimensions by taking tensor products. You already have done this exercise in going from Pauli matrices to Dirac matrices. If you ever go look at those Dirac matrices, you'll see that they have blocks, which are Pauli matrices, and that each block, even if you take your glasses off so you can't see the Pauli matrices, but the blocks themselves are arranged in sort of a Pauli-like form. That's another way of saying visual language. Tensor products of Pauli matrices are used to create these spinor matrices, the kind of Dirac matrices of higher dimensions. So you're not surprised that you sort of have these tensor product representations. Spinors of SO10 would somehow have to involve spinors of SO6 and these kinds of spinors in some way. And so it's not insane that it turns out that under these three groups, that the 16 is a 4, 2, 1 and a 4, 1, 2. Some left-handed 4s and some right-handed 4s. Okay. Now here's an easy one. SU4 contains SU3. And that's QCD. So 3 of these 4s, 3 degrees of freedom in the 4, are actually just the 3 colors of QCD. But then there's the 4th color, which we don't see, seemingly. But we do see it, because after all this breaking, it turns into the lepton. It's just the lepton. So, in this language, leptons are the 4th color of SU4. And this SU4 group is called the Pati-Salam SU4 because Pati and Salam introduced this unification of leptons as the 4th color of QCD. Okay? Generalization of QCD. Okay, there's one remaining thing that's worth noting in this SU4, which is it breaks up into a 3 and a 1, right? And there's a diagonal generator that looks like 1/3, 1/3, 1/3, -1. You see, it's traceless, which is what to be a generator of SU4, you better be traceless. And it's Hermitian, so that's good. And you can ask, who is this? Well, apparently it's giving 1/3 charge to each of the quarks, and it's giving -1 as the charge of the lepton. And so this is the generator of B minus L. Baryon number minus lepton number. The baryon number of every quark is, of course, 1/3, since there are 3 of them in baryon, minus lepton number. And so this contains U1 B minus L. So then the last thing to say is that you don't see hypercharge anywhere here, but indeed U1 hypercharge is nothing but a subgroup of SU2 right cross U1 B minus L. I forget the exact normalization. It's something like T3 right plus Q B minus L with some factors of 2. So there's the entire standard model sitting there. But indeed, I've now told you enough that you can work out the quantum numbers that we see in nature purely by taking this 16, this beautiful, simple representation, the spinor of SO10, and just decomposing it in all these ways. So work it out yourself, of course, magically it's that. So it's a deep insight into the standard model quantum numbers to just say, wow, boom, they came out of some group like SO10. Now there are other potential groups that we could have gone through, but I think we're pointing to something. What does that clue mean? We don't know what it means beyond that, for sure, but there is surely an exercise that has to be done. Because this one single gauge coupling has a predictive power it predicts, so G gut makes a prediction. It says that G of QCD should be G of electroweak, which should be G of hypercharge. If you're careful about the normalizations of hypercharge, U1s are tricky things to normalize, you find that the G1 here corresponds to root 3/5 of G. So if you like, humans found the Standard Model first, and they chose a normalization for hypercharge couplings, which was perverse and irrational, literally. And this is the right one. But now we can fix that, okay? Okay, so, but that prediction is obviously wrong. Let's not forget. But now again, we invoke the renormalization group to say, this is the prediction before you took into account all the large logs, this, that, the other, the running that takes you down to the scale at which we actually have measured the couplings. We have not measured them at the gut scale, wherever that is. And so we have to run these things down and do it. Now, great simplification at one loop is that the gauge couplings, all gauge couplings, have beta functions. They could be beta functions. You would imagine they're functions of all the couplings of the theory. Lambda, Yukawa couplings, all of these. But at one loop, because of gauge invariance, they can only be functions of this. At one loop. Nothing deep. I'm spending no more time on it. You can see that later yourself. But it helps because there's a kind of a closed form. In fact, the running of GI has this form. So it's easy to just say there are three decoupled renormalization group equations. They're easy to solve, and in perturbation theory, they all are order G cubed. So you work to leading order, and boom, you can draw it. And indeed, I'm just doing the standard model, by the way. Don't anticipate anything about Suzy and all that nonsense. Here is mu, or if you want, energies, right? But really, I'll do it on a log scale, because that's the way these things look like straight lines. And here we plot 1 over alpha for the three different types of couplings, and it looks something like, you know, what is it, 160. So alphas of 160 or something. And so these are the experimental energies, and you know, hypercharge does something like this, and Electroweak does something like this, and QCD does something like this. And this scale is, you know, something like 10 to the 14. By the way, there are 4 forces in nature. That's not gravity. Gravity doesn't have a dimensionless coupling, but it does have a dimensionless strength, which is roughly energy squared over m Planck. So it's interesting to also see what it wants to do. Okay. And I think it's doing logs here. That's something like this. It's drops very rapidly around here. Go work it out. Anyway, not bad. I'm not speculating beyond the standard model or anything, but this surely, if we're just assessing what clues we have, this surely deserves some attention. Just follow the standard model particle content, fermion quantum numbers, trying to understand all the crazy numbers that appear there. And it seems quite reasonable. And them, they don't meet. You'll hear a lot of people spend a lot of time telling you that they don't meet by 7 sigma or this, that, or that. That is not a testament. That is not a criticism. They mean it as a criticism of this theory. But this is not a criticism of this theory. This is a testament to the precision of experiments. Okay? Experiments are incredibly, incredibly good. And yet, okay, they don't meet naively at the gut scale. We should have this. Instead, we have this. It's not meeting at a point. But if you actually draw this properly and take a look, and you would never study, so you must forget all the theory that you've already learned before coming to these lectures. But once you do that, and you actually look at this, you would say, with so little input, just qualitative numbers, sharp numbers. And then the data points to this. Something must be going on. Okay? Not only that, this unification scale, well, it could have happened at 20 TeV, but it's happening awfully close to where gravity seems to be getting into the game, the same strength of gravity as the other forces. They're starting to compete with each other, and that's where it happens. Something must be up with that, okay? And indeed, that's my sense. If you study a little further the different ways, so the key to having predictive power was this. Okay? That you had an initial condition for the renormalization group, and then you take the standard model and run. This is what gave predictive power. No, the prediction was not satisfied. But the standard model maybe is not the final story. So, but it seems to be a good deal of the final story if you think this is significant. Okay? There are other ways to get this kind of initial condition for the renormalization group. One of them that I like the most, both because I find it plausible, but it's easy for people to understand, are called orbifold guts. I won't talk about them, but I find them in some sense even more plausible than the original grand unification. And but you can read about them in this review. Okay, there's one prediction, the smoking gun of the original grand unification, and yet not of orbifold guts. But the smoking gun of the original grand unification is proton decay. Proton decay is the analog for grand unification of weak decays for electroweak theory. We have weak decays, it's a factor of radioactivity. And that is if you didn't have the W boson, then you wouldn't have weak decays, and that would be a different world. Well, in grand unified theories, you have the analog of W bosons, and they give rise to proton decay, basically through, for example, there's something called the X boson. It's a colored particle. It is to guts what the W is for us, and it does this. This is, if time goes this way, I'm calling this is an antiparticle. This is an anti-up. This is up. And how does it mediate proton decay? Well, if you happen to have a proton, so here is a UUV combination, which is the proton, then, as time goes, you can decay into an anti-up and an up, which could make a pion and a positron, and that's proton decay. And anyway, there are various such processes, there are various experiments that look for this, and we know that the lifetime bounds on the proton is longer than the age of the universe, which we can say with confidence by looking at a heck of a lot, like the tail of the distribution, by looking at a heck of a lot of protons. But already, that seems to be at odds with the 10 to the 14 GeV. Better if it's 10 to the 16 or higher. But again, you should be forgiving. We have made vast extrapolations, and things are even vaguely working out. Vaguely working out, only a few orders of magnitude off the bounds. This 10 to the 14 GeV value for this X boson mass. So it's intriguing. Let's at least agree that it's intriguing. Okay. So there's one striking thing that you say, look, you decided to study the fermions.
if you looked at the gauge bosons, there wouldn't be complete multiplets. The gauge bosons of 3, 2, and 1 of the Standard Model do not fill out a complete representation of SO10. They fill out part of a complete representation of SO10. Okay? If you look at the Higgs boson, it doesn't fill out a complete representation of SO10. The Higgs doublet is not a complete representation of SO10. It is part of a complete representation of SO10. Why am I giving so much significance to these? Somehow I'm pointing to the fermions as fossil evidence of something that happened at incredibly high energy scales and survived into the infrared. Now, you can only judge that something is good fossil evidence if you sort of understand why it would stand over, it would not be corrupted over time. Otherwise, you have a feeling somebody placed it there yesterday. Okay? So to add a little bit to the evidence, you would like to know why fermions are such good fossil evidence. And that allows me to say again, secretly, everything I'm telling you about guts is to secretly tell you about the Standard Model. And so, but to say it in a significant way. So let's try to understand why fermions make good fossils. And that is the subject of gauge anomalies. Okay, so we saw that the existence of massless spin 1, or even spin 1 particles which have mass, but which you're planning the theory to extrapolate to very high energies, require gauge symmetries, and that you can think of the gauge symmetries as having to gain life by having these conserved currents, which ultimately turn into gauge currents. Okay? These conserved currents are not there by accident, they're there to protect the existence of light spin 1 particles. Okay, so we want this, we need this. But there are diagrams where these currents can appear. You want to think of these as gauge bosons. Now, there are various types of gauge bosons, so there are various, let me put indices on it, A, B, C, for all the different types. There's one different type of current for every gauge boson in the Standard Model, for every gauge boson in the grand unified theory. Now, these triangle diagrams, I'm only pointing you to their significance. These triangle diagrams are the central obstruction to satisfying these conservation equations. If you have already satisfied the conservation equations at tree level, then there is a potential obstruction to satisfying conservation equations at loop level. And this is the loophole. This is the obstruction. Okay? So the word anomaly means that everything classically or at tree level looks great. You have the symmetry, there's no problem. But as soon as you want to quantize the theory, you run into an inconsistency with having the quantum theory and the conservation of currents. Typically, you can keep a subset of the currents conserved, but then some other current is not conserved. If these currents are gauge currents, you cannot afford to have a current which is not conserved. Conservation of the gauge current is gauge invariance. Gauge invariance is the ability to have this light degree of freedom, spin 1 degrees of freedom. So it's absolutely crucial that gauge currents are all conserved. And the study of these diagrams leads to the condition for conservation of these currents, which you should learn about and can be learned about. If you take the 16 language, by the way, in figuring out the quantum numbers to be in the 16, you have to use charge conjugation to make all of the fermions of the Standard Model left-handed. Okay? So don't work in terms of the right-handed positron, work in terms of the left-handed, the right-handed electron, work in terms of the left-handed positron. So in this completely left-handed notation, where let's just talk about the 16 just quickly.
the general rule for anomaly cancellation, which is to say that whatever dangers these diagrams pose is cancelled, is this. You take all the fermions that are in your theory and write them as a column vector, and then you have charges for all the different types of gauge groups, and all the different types of gauge particles have their own associated conserved currents and their own associated charges, which are quantum numbers of these fermions. So these are the fermion quantum number matrices. These are matrices. If you have 16 fermions or 15 fermions, they are 16 by 16 matrices. And you calculate, and this is the commutator here, and so you calculate this trace. And if it equals 0, then you're good to go. All the currents are conserved, life is good. So first, you're not surprised if I tell you that in fact life is good. That if you take the standard model particle content, fermion content, put it in this big, make everybody left-handed using charge conjugation where necessary, putting them in a 16 and writing the charge matrices, just putting in the charge quantum numbers in these big 16 by 16 matrices and calculate this at 0 and it's good. But here is the exercise you can do. Each generation of the standard model, since they're just replicas, in terms of the gauge quantum numbers, they're just replicas of each other. Each generation obviously satisfies this independently. Because they're just copies, 2 copies, that's it. But the exercise is prove. So the question of why are there 3 generations, I'm not asking that here. It's an interesting question. I'm not asking that. But I am asking the question, given that the X boson of SO10 was heavy, but the W boson was light, given that breaking of grand unified symmetry allowed the breakup into heavy and light among the gauge bosons, presumably the same thing happened with the Higgs bosons, that only a fraction of a multiplet of SO10 has survived in the infrared. Why didn't the same thing happen to the fermion content? Why did an entire representation of SO10 come down? In fact, 3 of them. So prove that anomaly cancellation, and I again mean gauge anomaly, I'm not talking about global symmetries, but gauge anomaly cancellation, fails if only some of a fermion generation is present in your theory, the theory that you're trying to extrapolate, meaning light. Now, there are many possible, I could take the quark, I could take the right-handed up quark multiplet, quark, 3 colors of right-handed up quark, and imagine that somehow they were heavy for some reason, and everybody else was light. I can consider all possible combinations, so there are many different things that could be heavy and light. But you can go through the exercise. Anomaly cancellation is so powerful that it says that everybody together or not at all. It's possible that you only ended up with 2 generations, even though the gut theory had 3 generations. Maybe something happened, then boom, it's gone, and you ended up with 2 generations. It's easy to figure out a model that would do that. But you can't figure out a way where only a fraction of a generation of these spinner representations of fermion shows up. At least the spinner representation has this tightness to it. And so in part, this tells you why fermions are such good fossil evidence. Because the anomaly constraints are so tight that it's everybody or not at all. Of course, there didn't have to be a gut in the first place, in which case the fermion content could be very different. So we should consider that fact and also pay close attention to the anomaly cancellation. How tight is the plot of the standard model? Okay, now everybody knows So it's almost, we're not worth saying that there is such a thing as supersymmetric standard models. And the plot, so in SUSY, or if you like the MSSN, not only do you add partners, superpartners for all the particles present, you also are forced to have two Higgs doublets and Higgs zeros. In fact, there are a couple of reasons why you need two. An easy one, since I'm standing right here pointing to this diagram, is one Higgs doublet would have one Higgs zeno, and one Higgs zeno would suffer from this kind of gauge anomaly. Two Higgs zenos don't. So anomaly cancellation is already critical even in the MSSM, but it forces you to add not just superpartners, but an extra Higgs multiple altogether. And exactly this particle content, if you put in the data that we measure, introduces kinks basically at the, so this is the scale at which we've measured couplings, let's call it MZ. This is the scale at which we hypothesize that there are some SUSY breaking, so basically superpartners live here. And what would have been the behavior of the beta functions changes, they get kinked a little bit. I hope I'm drawing the kink in the right direction, I'm probably not. This looks more impressive than I actually see. Anyway, so this is 10 to the 16 GeV, which is marginally okay. Gravity is not too far away, and the picture looks so much better. In fact, if you do this in one loop, it looks so good that it just, that's it. You have this must be the picture. Now, even if you buy that, you would say, look, exactly where I put the SUSY threshold, it's not that easy to say. If it was a 10 TeV, which would make the LHC not that useful, the picture would look just as good. If it was 100 GeV, which would have made many past experiments more motivated, it would also be this good. So it's kind of looks very nice, but it doesn't tell you exactly where things. It's not like you can say exactly where this kink in the normalization group should be. But surely it tells you that life is very exciting. There's something to come. That the gap is not very big, is what it tells you. The gap that we're worrying about being big is not very big. This is the evidence. Now, if you actually go, or there's a massive coincidence, right? There's a massive coincidence. This beautiful theory of supersymmetry, natural generalization of special relativity, there's ain't never been anything like it, is when we just put it with the standard model and the data, it points to this, and it's just a coincidence, because it's actually the wrong theory, and this is just a total coincidence. That is possible. In fact, to assess that kind of question based on this belief, that this is just too good, this is again circumstantial evidence, but if that was really a point with zero measure, then that would be pretty good evidence. But there's some error bars surrounding this. And two-loop running is important. Things don't look like straight lines. Threshold corrections are important, and so on. And so one way of phrasing it to assess, if you want my executive summary of where we stand today, one way of phrasing it is, in each case there's some amount of running. It's not the overall running that matters of each of these things, it's sort of the differential running. The differential running is some measure of how these three slopes are different, which allows things to converge. So a crude statement is that in the standard model, there's a certain amount of differential running that you can just calculate by standard model beta functions. But you need, of course, it doesn't work. You don't end up at a point. There's some blur. So you need some fudge factor.
Some other piece of physics has to come in. If you believe in standard model unification, some other piece of physics that's not included in just the beta functions has to come in and correct the answer. Okay? And the answer is that it needs about 20% of the differential running fudge factor in order to say that that is the theory of the world, non-supersymmetric standard model. If you do the MSSM, then the answer is more like 4%. As I said, the standard model is not bad. Each of them needs a fudge factor. In the MSSM, with two loop running, it doesn't work perfectly. So you need some fudge factor, and it's about 4% of the differential. This is like 1/5 smaller than that. It could be that basically the standard model is got it pretty close to right. And that any new physics that you add, as long as it's not some major destruction of the standard model itself, that adding something to the standard model, it'll change the slopes of beta functions, the slopes a little bit. And if you're just 20% lucky, it'll be an improvement of how much of a fudge factor you need, and if you're 20% fine-tuning in probabilities, it'll work. So this is the kind of worst way of talking about the MSSM unification. It's got so many deep principles that one feels bad to say it. But if it's this picture that's driving you as at some point in the field, this had enormous psychological effect. And for some people it still does, some fraction of it. Maybe. My own take is this unification that we see in the standard model is just the data and the minimal standard model. The particles we've already seen. I take it seriously. Something is up. You don't have to buy that. And therefore, I find it hard to pursue ideas where you throw away, you change what your view of the ultraviolet is so that this fact that the standard model data seems to be pointing to something is a complete coincidence in your new worldview. So I say, try to think about, gamble more money on new possibilities which don't kill this beautiful fact. This is even more striking. So, this is more striking. But this is a success built on this success. The extra that you get. So I tend to say, it's okay to think about things which are not SUSY MSSM. It's okay to think about them. Because it's possible that this success over this is a coincidence. You should also put a lot of money on the fact that this is actually true. This is really pointing to some true statement. And so you should put some money on that too. So taking SUSY very seriously is very important. That still allows many different possibilities in high detail. And also taking SUSY as the wrong direction, not ultimately wrong, maybe it plays a role somewhere or somewhere, but to think that it's not directly relevant to the LHC is also quite plausible in scenarios where at least this success is maintained. And then, if you're pursuing an incredibly exciting idea, where all of this data has to be thrown away as pure coincidence, but it's incredibly exciting, I think that's worth doing too. Okay? But you put less money on it. Unless you're approaching the end of the LHC and you see nothing, and you are trying to look in every drawer for something that is, evading you. You look everywhere that was motivated, and then you want to look at the last place, and where you're looking would be ridiculous if you really believed in the paradigm of grand unification. Go ahead and look at it. Okay, so that's my order of priorities. Okay, I wanted to switch to two topics. See, next lecture, I want to switch to doing magic. Okay, I've had enough of being good and reviewing the standard model. So I wanted to, however, do my duty. It was very hard to give this lecture because I really wanted to switch and just do the magic today. But So let me start at least by pointing to the need for some magic just in what are the puzzles of the standard model. Anybody looking at the data with fresh eyes, that is, really come from another universe and look at it, will see some puzzles, and those puzzles are very exciting. We've already talked about some puzzles. I've given you a kind of first glimpse of what I'm calling the hierarchy problem, or why the weak scale is so much smaller. There's no digital protection for a light weak scale. Okay? In fact, that's what I'll start off next lecture as magic number 1. Okay? That there is in fact a region of standard model parameter space where the weak scale has digital protection. It's the same standard model, just look in some different part of the parameter space. So, because that sounds impossible to believe, that's why I'm calling that. So that's what I want to start with next time. Let me see if I can get through this. Okay, fine, there's that. Now, there are these gauge couplings. And self-coupling. And so there are a number of couplings of the standard model. Suppose you've never seen the standard model. You come to this universe, somebody says, here's the structure of the standard model. I haven't measured the parameter space. You look at, you see a bunch of dimensionless numbers. What is your best bet for what they are? 1. Okay, so, good. Standard model plays by those rules. There it is, a bunch of numbers that are 1. But, then there are a bunch of Yukawas which are not the top Yukawa. And they're all much less than 1. And furthermore, if you look at the pattern, they're very hierarchical. Of course, we don't see, we infer the Yukawa couplings and bounds on them. We see the masses. Not only that, you of course can see the CKM angles, which are also manifestations of these Yukawas. And so from the masses and the CKM angles, clearly there's some very hierarchical structure there. And these CKM angles are, of course, what I'm about to say next. There's mass eigenstate I, there's mass eigenstate J. They have weak interactions with each other. And there's an angle here, which is theta ij. Okay, we all know that. That's the CKM angles in cartoon form. And if you look at this hierarchical structure here, so one is why is that happening? Why are numbers which are not my best guess 1 happening? But if you look at these numbers, you see some sort of pattern. And it is not the Balmer series, so that you just write out the formula and then you're done, and you can start to say what is the physics underlying it. But there's no question that there's a pattern, and it's a fuzzy pattern, and I want to give a useful summary of the data by giving an ansatz. See, we don't see the Yukawa coupling, so I'm not giving you a proof of anything. But the up and down Yukawa matrices, the data is consistent with Yukawa matrices of the following fuzzy form. If you want to quickly tell the aliens from this other place what the data looks like without reading out everything to 2 decimal places or something, what's the quick thing you would transmit to them? Okay? In the old days of writing telegrams, you don't want to write everything. So first of all, I have some order 1 uncertainty in these matrix elements because I don't have a precise formula. So if this was it, by the way, if this was the answer, this would be great. All your bets would have been true. Everything would just be dimensionless order 1 numbers. Perfect. But that's not true. So, and this is just the fuzziness. There are some small things. Okay, there's some hierarchically small things. But the data is nicely summarized in terms of sort of 2 small things. One which is sort of a left-handed small thing, which controls the I index, the left-handed index, and the other is something that controls the right-handed index, so it's 2 sets of small things, or if I happen to be doing downs, I would do that. And so there are these nine numbers. And epsilon 1 is smaller than epsilon 2, the smaller, much smaller is in the eye of the beholder. So, you can see the hierarchical structure as being something like this. The best way to convince yourself of this is to not look at the data, and try other ansatz. I'm just giving you one that seems to be roughly consistent with it. You can go ahead and play with this yourself, and you'll find that if you work perturbatively in the epsilons, that the CKM matrix Ij, say if I is less than or equal to j, and simply the other way around, goes like something of order epsilon I q left over epsilon j q left. Look, I'll let you do it. I don't want to waste time. It's a fun exercise to fit the data to this. But starting from one root observation, that if the epsilons are somehow all less than or equal to 1, to get the top Yukawa, which is 1, presumably y33 is 1 because each of the epsilons involved is order 1. So the fact to get y top to be order 1, then we would want epsilon 3 q left and epsilon 3 u right to be order 1. Okay. But all the other epsilons should be small. And just see, you should see that you could roughly, crudely fit all the data. And you might say, yeah, I can fit it, but I'm not getting convinced that there's anything to this ansatz. Well, go ahead and fit it and you'll see that in some sense it resonates with the way the data looks. I'm only trying to give voice to what any person, unbiased by this ansatz, looking at the data, sees. Different generations, the more different the generations and the more deviant in mass they are, and the smaller the mixing angles between them. And this is an ansatz that quickly does that. Okay, so quick summary of the data that I sent. If you go to the leptons, however, this is quarks. If you go to leptons, then you of course see m electron is much less than m mu1. You see hierarchy there. And there was a point in time where this was the data, because we didn't see neutrinos were massless as far as experiments were concerned. This was it. So first there's a puzzle. Why is something like this sitting in the data? There's something going on in the quarks. The charged leptons, something very similar is going on, except it looks like the neutrino is massless, so that kills some of the subtlety of CKM. But then we go and find neutrino oscillations, masses, we confirm oscillations, we do a lot of experiments. And indeed, the neutrinos are, of course, that of course is obvious, right? And but if you look at the simplest ansatz for the Yukawa couplings in the neutral sector of the leptons, the simplest ansatz is that it is very small overall, but not with any ij here, multiplied by sort of order 1. Again, this is a crude cartoon. Many people see what pattern they want in the neutrino masses. So you will find people doing discrete group theory, this, that, the other. Here is a first pass. This is, everybody should agree at the first pass that what you're seeing here in the neutrino sector is something that's small. In that sense, it's hierarchical because it's smaller than everything else you've ever seen. But relative terms all look more or less randomly chosen. It's not easy to sort of pick out a pattern. The idea that this is sometimes called anarchic structure to the neutrinos, and the paper that tries to argue that it is rather consistent with anarchy is this paper. And indeed, there remains, so this is a mystery. many people, before this data was solid, many people said, I expect hierarchical leptons and I expect hierarchical neutrino structure. But they didn't get it. It's a surprise, it's a shock. Okay? People who were constructing theories of this sector suddenly got blown away by this sector because everything was supposed to fit together. So this is a puzzle. Why the sudden switch in behavior going from quarks and leptons? Especially if you think of quarks and leptons. The leptons are the fourth color of the quarks in some sense, right? So it's puzzling, but there's a puzzle, okay? Even the nature of neutrinos could be like the rest of the fermions, getting good renormalizable Yukawa couplings coming from this kind of structure. But because the Higgs has exactly the same quantum numbers as the left-handed leptons, the right-handed neutrino has to be sterile. If it's a Dirac fermion at the end of the day, it should be sterile under the standard model, which of course beautifully fits into a 16 of SO10. But there's another, given how small these neutrino masses are, there's another possibility, which is in fact this. A non-renormalizable coupling, but where the non-renormalizable coupling, if you want the coupling constant, this dimension -1 operator, is incredibly weak. So that the scale at which the theory blows up because it's non-renormalizable, lambda, is incredibly high. So that this so-called option of giving mass to the neutrino, the so-called Majorana mass of the neutrino, I think should marginally be more favored in people's prejudice than this, for various reasons. But it does not mean the breakdown of the standard model at low energies, because this scale is so big that you can imagine extrapolating the standard model to very high energies anyway, because the breakdown scale is large. Okay? So but which of these is true? We're trying to figure out the pattern. This is so-called flavor puzzle, different flavors of fermions, and all the hierarchical structure. This is a flavor puzzle, and one aspect of the flavor puzzle, in order to even look at this data, is which variant of neutrino mass are we looking at experimentally? And so, indeed, there are experiments trying to probe this to try and see experimentally in processes where you have weak interaction decays, beta decay. You can also have processes which have double beta decay, where you have two electrons, and two neutrinos being shot out. In the Majorana case, one possibility is that the two neutrinos, even it's not neutrino antineutrino, it's neutrino-neutrino, and this mass term allows them to annihilate like that. And so you end up seeing two electrons in these double beta decays, two electrons but with no neutrinos. Whereas in the Dirac option, since neutrino number is conserved, this would be impossible, and you would never see that. And so looking for neutrino double beta decay is a critical experiment, trying to probe which of these two options answering this puzzle. Okay. Let me just say, I think this is very quick. Obviously, after the Volansky lectures, you are perfectly aware that dark matter has a very strong case to be made that it is there, and secondly, that it is not constituted out of the standard model. Okay. So, dark matter exists, it's not the standard model, and hence, something about the standard model is incomplete in that sense. It's possible that this dark matter is very decoupled from the standard model, or if it's coupled to us, then the gap is over. Because if it's coupled to us in some way, then this hypothesis that there's a gap with the standard model and nothing else is clearly wrong. Okay. But there is a mystery that I still take as very serious, meaning I'm very inspired by it. And that is that the cosmic density of dark matter today is very squiggly, roughly, in fact, a factor of 5 only, different from the
density of everything in the standard model in the universe today. And this is very squiggly. Maybe I should put it this side then, this squiggly is better. And this is whatever is making the universe accelerate today as an energy density, if you want. This coincidence is also a striking puzzle of the world, okay? But it's a striking puzzle beyond the standard model. Dark matter has pushed us beyond the standard model, necessarily. There's something going on beyond the standard model. No. If it's so divorced from us, it was really a terrible, very divorced. It is, if you run the movies of cosmic history and different possible laws of physics, you rapidly see that energy density, which is some, mass to the fourth power, it easily happens that vastly different densities of different types of constituents of the universe can arise. Why is it that today these are comparable? Is a puzzle. Okay. Now there are attempts to answer it, but you should keep in mind that there's no absolute front runner, and this is a very interesting puzzle. For people who think that dark matter is completely different from anything to do with the standard model, why is it only a factor of 5 different? I think the last one is just this. I think that I completed that part, which is just that there's one more coupling that I haven't mentioned in the standard model. One more dimensionless coupling. And that is the so-called CP violating theta parameter of QCD, where you write the QCD gauge field strengths, but instead of writing, say, the standard kinetic term like thing, you put in the epsilon tensor node. Now, this is a beautiful story. You must learn it. You miss out the fun in life if you don't understand the history and power of this term. It is a total derivative. If you start drawing Feynman diagrams and saying, what's this vertex, then it becomes trivial. The non-perturbative story of how this is still what physical effects, and how we have such command over the strong interactions that we understand, QCD. Given a combination of QCD theory and then data, the data is helping us even though we're too stupid to just analytically solve everything. And telling us that we ought to be sensitive to this parameter, even though in perturbation theory you could throw this whole thing away. And that this parameter, again, what should it have been? I come from another universe, please tell me. Well, it should have been order 1, presumably. But it's experimentally incredibly, I forget the example. It's incredibly 10 to the minus 10 or something. It's incredibly close to 0, or consistent with 0. I mean, we have not seen any sign of this. And it would show up. What it would do is it would take the strong interactions, which are, you can think of as an isolated sector. The strong interactions, like QED, are normally charge conjugation and parity invariant. They're very symmetric theories. It's only the weak interactions that are so crappy, but charge interaction and parity invariant. This would kill that because it's CP violating. And it would be CP violating in a big way. This is not some tiny, this is a big thing. There's a phase, of course, your famous phase in the CKM matrix that's physical. It's actually order 1. But by the time you figure out what's the physical observable that's sensitive to it, it gives you incredibly tiny effects. Okay? This thing is not. If it's order 1, it's big effects. That's how we have such incredible sensitivity that tells us it's consistent with 0. And there's a question, why is it, experimentally, why is it equal to 0? And so this is the last major puzzle. There is a beautiful theory of why it might be. It's called the axiom, but it's physics beyond the standard model. It's not trouble-free. It comes with its own preconditions, which are not trivial to satisfy. But it's a very beautiful theory, and these Tassi lectures by Dine are a place to read about. He's written a number
more than one review, Cassie, his axial lectures would tell you a little bit about. It's a very beautiful field theory story, why you know that this thing should have consequences in the real world if it were non-zero, and hence there's a puzzle. Naively, you would never have thought about it because of our perturbative vacuum. Okay, let's stop. One small